In this video, we would like to prove that the sum of the first n cube numbers gives us this formula. 1/4 n squared brackets n plus 1 squared. We're going to prove this by induction, and like all good inductive proofs, we need to start with the case n equals 1. So let's write this down. N equals 1. Well, we just need to work out the left-hand side and the right-hand side by computing them. So the left-hand side is just the sum from r equals 1 to 1 of r cubed. This is a really easy sum for us to work out. It's just one term, and the one term is 1 cubed. So the answer is definitely just 1. If we think about the right-hand side, when n equals 1, we've got 1/4 times 1 squared, which is just 1, times 1 plus 1 squared. It's going to be 2 squared. Well, this gives us 1/4 times 1 times 4, which just simplifies down to 1, doesn't it? So what we've seen so far is that this result is true when n equals 1. We write this down. So true when n equals 1. The next step in an inductive proof then is saying, well, if it's true when n equals 1, we're going to assume it's true for n equals k. That's the next thing to write down. So assume true when n equals k. I think it's a really good idea here if we write down what we're actually assuming to be true. And being careful with our k's and our n's, we're assuming that the sum from r equals 1 to k of the r cubes is equal to 1/4 k brackets k plus 1 squared. Okay, on to our next step in the inductive proof then, is us saying, if it's true for n equals k, like we've assumed, we would like to show that it's also true for n equals k plus 1. So when n equals k plus 1, I'm going to write down first of all what we would like to show. This should be in a different colour because we can't say it's true yet, but it helps us to know what we're aiming for. So let's have a look. We would like to show, or we want, well, what we want is the sum from r equals 1 up to k plus 1 of the r cubes. We would like this sum to be equal to 1/4. This should be a k plus 1 squared here. Can you see all of our k's from before will shift up to a k plus 1, and our k plus 1s will shift up to a k plus 2 squared. K plus 1 has gone to k plus 2, k has gone to k plus 1. This is what we would like to show. The way we're going to do it is with this really common idea in proofs by induction. And it goes like this. Well, we already have the sum from r equals 1 to k. But we want the sum from r equals 1 to k plus 1. And this, I should write what we're actually finding the sum of the r cubes. The sum to k plus 1 is equal of the sum of the r cubes to k plus an extra term on the end. So we've taken the sum up to k, but we also need to add on this final term, and the final term is k plus 1 cubed. This sum to k plus 1 is just the same as this one with that last term added on the end. Well, let's use the result that we've assumed to be true for this series. And namely, it's this one at the start, isn't it? So this should be 1/4 k, k squared, k plus 1 squared. And we need to plus our k plus 1 cubed on the end. Well, now if you've seen my other video on proving the sum of the square numbers, you might be familiar with this kind of trick. First, we look for what's common in both terms. We've got a k plus 1 squared and we've got a k plus 1 cubed. We definitely need to take that out. So k plus 1 squared must come out of both of these. And we're thinking then, what will be inside these big brackets? Well, k squared for sure needs to be there, because that's left over from this term. But being clever, we like to take out this factor of 1/4. So this should come out at the front. And the reason for that is, like before, it's much more helpful for us to have whole numbers in the square brackets. If we took out a factor of 1/4 then, that means we need a 4 in with this leftover k plus 1 to make up for it. So we need plus 4 lots of k plus 1. Can you see? Our 4 and our 1/4, they cancel out to give us just a 1 there, and we still needed the extra k plus 1 in brackets. At this point, we should be expanding out this thing in the square brackets. So let's have a look. 1/4 brackets k plus 1 squared, and in the big square brackets we've got k squared plus 4k plus 4. Oh, this looks really interesting to us because it is a quadratic that we can factorise. And if we have a look, we should have 1/4 k plus 1 squared. This thing, k squared plus 4k plus 4, factorises really nicely to k plus 2 squared. Okay, well now if we consider, that's exactly what we wanted earlier, isn't it? We wanted to show that the sum to the k plus 1th term gives us 1/4 k plus 1 squared k plus 1 plus 1, which is k plus 2 squared. That's exactly what we needed. So hence, if the result is true for n equals k, then it's true for n equals k plus 1. If I can write, then true for n equals k plus 1. And since we already knew that our result was true for n equals 1, that means it must be true for n equals 2. And therefore it must be true for n equals 3 and n equals 4, and so on. So to conclude for us, we can say, so it's true for all the n's, so true for all the n's in the natural numbers from 1 onwards. And we write it again like this, n with a curly bracket, like a curly e thing, to show it's contained within this set of natural numbers. We write as an n like that. So for all the n's that are natural numbers, we know this result is true.